Hi Pre-Calcers, welcome to Lesson 9.3, Polar and Rectangular Coordinates. This is really a central theme for this whole chapter, so hopefully it'll go pretty well. Again, our main task, as you can see, is to convert from polar to rectangular coordinates and vice versa. Here's a guy known for beating up people, I think, but supposedly rumor was it that he was converting to Islam, so not quite that same conversion, but you get the idea. Alright. So, really a couple of different ways to convert. We'll show you an algebraic method based on these formulas here, and we'll also show you probably the method that I prefer is once again drawing triangles and labeling them and kind of reasoning it out a little bit. Now here's three equations that help us out immensely on these conversions. They're based on things that we could draw on the circle chart. Might talk about a little bit more in class, but we'll use these to do some nice conversions. Here's our first example. This is in polar form right now. We would like to convert this to rectangular form. And remember that this is our r value and this is theta, of course. So really, according to the algebraic example, to get x, all you have to do is take r, which is 4, times the, you know what, I goofed these up. Come to think of it, this should be reversed. How dare I make that mistake? But anyway, this should be 4 times the cosine of 30. And if you remember from your circle chart, the cosine of 30 is the square root of 3 over 2. So 2's cancel out, so I'll get 2 times the square root of 3 for my x-coordinate. My y-coordinate then would be 4 times the sine of 30. And the sine of 30 is 1/2. So 4 times 1/2 is 2. Therefore, my ordered pair here, I'll try to write it up here, I guess, would be 2 times the square root of 3, comma, 2. That's the algebraic way of doing it. Let's think about drawing a triangle to do this. Now, you would be wise to remember some of our special right triangles, the 30, 60, 90, and the 45, 45 right triangle, and those relationships that they have. So anyway, this would be 30 right here, let's say. And remember, 4 is like the hypotenuse as the crow flies, so to speak. Now you may remember that on these special right triangles, I'm going to change colors here quickly, especially this is going to be one of these 30, 60 right triangles. The side opposite 30 is half the hypotenuse. So in this case that would be 2. And the side opposite 60, that would have to be this side right here, would be half the hypotenuse times the square root of 3. So sure enough, we get the same answer, 2 times the square root of 3, comma, 2. Either way is fine. Whichever method you prefer, you can use. Okay, next. Converting from rectangular to polar, a little trickier, but still not too bad. If I were to convert -4 to a polar coordinate, I'm going to write this one out, I think. I'm going to, first of all, draw a little grid here. I do want to try to get it in the right quadrant. So -4, -4 would put it down here. This is a right triangle, of course. I'm going to label this side as 4 and this is 4. And then you may remember that when we look at a right triangle like this, when both sides are the same, that it actually is a 45-degree angle here. That's a 45, 45, 90 right triangle. And how do I figure out my hypotenuse there? Well, you could use the Pythagorean theorem, 4 squared plus 4 squared. So 16 plus 16 is 32. The square root of that is the same as the square root of 16 times the square root of 2, or 4 times the square root of 2. So that's my r value. So if I was writing this as a polar coordinate, it would be 4 times the square root of 2, comma. Now I can't use 45, remember, because my angle is more than just that little reference angle. My angle starts here and swings all the way around to there. So that's 45 plus another 180. So that would be 225, I believe. So there is my polar form for that particular coordinate. So that's how to convert from rectangular to polar. Again, we could use an algebraic way as well. Now let's get to one that's maybe a little trickier, -5, -2. So again, I'm going over here, -2, my triangle looks like this. Now clearly this is not a triangle that is one of these special right triangles, unfortunately. So then the question becomes, how do I figure out what this reference angle is right here? Well, if I think back, I can use my inverse stuff like we said, and so the inverse tangent or the arctangent of opposite over adjacent, I'd have to say 2/5 in this case, and I am in degree mode, and when I do that I end up with about approximately 22 degrees. And I still then have to figure out my hypotenuse here. So this is going to be 2 squared plus 5 squared will give me that r squared value. So that's 25 plus 4 is 29 is r squared. So then the square root of 29 would be r. So if I write this particular one in polar form, it's going to be the square root of 29. That's my r value. Now what about my theta? Again, it's not just 22, but it's 180 plus 22 to get it in that right quadrant. So 180 plus 22 should be simply 202 degrees. Again, we could write this in radians perhaps as well, but probably more familiar with degrees, so that's what we'll use right now. Another example. This time now we can look at not just coordinates. Remember, up to this point we've just been converting coordinates or points back and forth from polar to rectangular. Here we're going to actually use equations. Once again, we have these same conversions that we've seen before that will help us convert between rectangular, which has the x's and y's, and polar, which has the r's and theta. So our first example here, let's take a look at it. Write r equals -3 in rectangular form. So again, when they say rectangular form, we want to have x's and y's in our final answer. Well, our main substitution there for r, as you can see up here, is in place of r, I'm going to put in the square root of x squared plus y squared. That's going to equal -3. Now I can simplify this a bit by squaring both sides. So if I do that, I'll get x squared plus y squared, and if I have -3 squared, that's going to give me +9. And basically, that's it. I'm done. Because now my equation has an x and a y in it. Doesn't need to be solved for y or x necessarily. And this is actually a famous equation we'll probably learn about in January. This is an equation of a circle. You remember that r equals any number that's going to be a circle when we graph it polar-wise. Same thing here. X squared plus y squared, whatever that equals. This graph of this will be a circle. Just another way of writing it. All right. Next one. This looks a little trickier. Write this in polar form. So what do I do here? Well, first of all, I'm going to get a nice color to use, like orange. And so I'm going to make that substitution. Whenever I see x, I'm going to put in r cosine theta. And so that has to be squared. And whenever I see y, that's going to be r sine theta. This time -1, and it has to be squared, equaling 1. This will test your algebraic mettle here to do this. Now squaring this first part, I should get just r squared cosine squared. Second one, notice this is a binomial, so when I square it, I'm going to get the first thing squared, which is what this is. I'm going to get the last one squared, but then I'm going to get that middle term, which is this times this times 2. This times this times 2. So that's going to give me 2r sine theta, like that. And all that's going to equal 1 again. Now I can group some stuff here a little bit. Notice I have that cosine squared plus an r squared with the r squared multiplied by it. So I can kind of group those together. Cosine squared plus sine squared, like that. minus 2r sine of theta, and that's going to equal 0. Notice if I have a 1 here and a 1 here, I can just subtract 1 from each side and get 0 like that. Now, we all know from last chapter that whenever we have sine squared plus cosine squared, that's going to equal 1. So what I really have then is r squared minus 2r sine theta equals 0. I'm almost done. I'm just going to, usually we wouldn't do this, but I'm going to put each of these on a separate side of the equal sign there. Remember, I'd like to be able to solve this for just plain r. I'd like only one r in there somehow. So now, sometimes this isn't legal, but it is here because I know that r is not 0. I can divide both sides by r, and then I get my answer to be r equals 2. The r's did cancel out on this side because everything's multiplied and divided, so r equals 2 sine theta. There it is. So now we have just converted an equation that's in rectangular form into one that's in polar form, and that was great fun. Alright, so thanks for watching, everybody. This is a central idea in this whole chapter, and we'll be working on it when we get to class. Bye now.